Now we'll move on to the oxygen hemoglobin dissociation curve. Now it is a graph relating percentage hemoglobin saturation, partial pressure of oxygen in arterial blood. So when I have to plot the graph, you just simply make a graph. On the x-axis you make the partial pressure of oxygen, and on the y-axis you make the percentage saturation of hemoglobin, and you draw a sigmoid shaped curve. Now you have to draw 3 points in this curve. One is the partial pressure of oxygen in arterial blood, one is the partial pressure of oxygen in venous blood, and one is the P50. So at this there is 98 to 99% saturation. Here we have saturation of 75% in venous blood, and P50 is saturation of 50%. So the partial pressure is 13.3 kilopascals here, is 5.3 kilopascals in venous blood, and is 3.5 kilopascals at P50. What is P50? P50 is the partial pressure of oxygen at which hemoglobin is 50% saturated. So when you draw this graph, you have to show all these 3 points. Now I'll tell you the normal values. The arterial PO2 normal is 13.3 kilopascals and saturation is 98 to 99%. Venous is 5.3 kilopascals and saturation is 75%. And at P50, we have a 3.5 kilopascal partial pressure of oxygen. Now why is the shape of this ODC, oxygen dissociation curve, sigmoid? What is the reason of this sigmoid shape of this curve? We have studied this before. Initially, the hemoglobin is in a taut form, so it has a decreased affinity for oxygen, and when there is subsequent binding of oxygen molecules to hemoglobin, it turns into a relaxed and there is increased affinity for oxygen. So this can be seen in the graph in the way that initially there is a slow rise percentage saturation with increase in PO2 because the hemoglobin is in relaxed form, but subsequently as it moves into the taut form, there is sudden rise in hemoglobin saturation, and finally when the 4 molecules of oxygen bind, the graph sees a plateau. So this is responsible for the sigmoid shape of the curve. Now what are the factors that cause a shift in ODC? So whenever there will be an increase in affinity for oxygen, the curve will shift to the left, and wherever there is decrease in affinity, the curve will shift to the right. So factors causing left shift are alkalosis, decreased 2,3-DPG, hypothermia, carboxyhemoglobin, and methemoglobinemia. And right shift is caused by acidosis, increased 2,3-DPG, hyperthermia, pregnancy, anemia, acclimatization to altitude, and hypercapnia. And left shift is caused by hypocapnia. So these are the factors which affect the oxygen dissociation curve. Now what is Bohr effect? This states that increase in PaCO2 levels decreases the affinity of hemoglobin for oxygen. What is double Bohr effect? This is simply the Bohr effect operating in both the fetal and the maternal circulation. In the mother, there is increased PaCO2 and decreased affinity of hemoglobin for oxygen, which leads to oxygen unloading. And in the fetus, there is a decrease in PaCO2, which leads to increased affinity and thus oxygen loading. Thus the Bohr effect ensures that the oxygen can be transported from the mother to the fetus. What is Haldane effect? Haldane effect states that oxygenated hemoglobin has decreased affinity for binding to CO2, and deoxygenated hemoglobin has increased capacity to carry CO2. Now we'll talk about myoglobin. Myoglobin is an oxygen carrying protein found in skeletal muscle. It is a monomer, unlike hemoglobin, which is a tetramer. So it is a single polypeptide with heme. It can only bind to one molecule of oxygen, and it has high affinity for oxygen. So if we draw a curve for hemoglobin dissociation and myoglobin dissociation, so it will look somewhat like this. This is the oxygen dissociation curve for hemoglobin, and this is the oxygen dissociation curve for myoglobin. So here you can see that myoglobin has a higher affinity for oxygen than hemoglobin.